The story of the universe begins in a moment so profound, so mysterious, that even the most brilliant minds of physics and cosmology struggle to fully comprehend it. This is the moment of the Big Bang, the prevailing theory that explains how everything we know, the stars, the galaxies, the planets, even life itself, emerged from a state that defies ordinary imagination. To appreciate the grandeur of this event, one must step back and attempt to picture nothingness, not empty space, because space itself did not yet exist, not silence or darkness, because neither time nor light had any meaning. Instead, the universe was compressed into a singularity, and unimaginably dense and hot point, smaller than an atom, containing all the energy and matter that would ever exist. About 13.8 billion years ago, the singularity experienced a sudden expansion. It wasn't an explosion in the traditional sense, where matter bursts outward into pre-existing space. Instead, it was the expansion of space itself. The singularity didn't hurl material into a void. Rather, the void itself unfolded, carrying matter and energy with it. Space-time stretched from a near-infinite density and temperature, beginning the grand unfolding we call the universe. At the very first fraction of a second, timescales lose ordinary meaning. We are speaking of intervals as short as T-43 seconds, the so-called Planck time, when the laws of physics as we know them may no longer apply. At this earliest instant, gravity, electromagnetism, and the strong and weak nuclear forces may have been unified into one fundamental force. Theories like quantum gravity and string theory attempt to describe what happened in this primordial era, but humanity has yet to find a complete explanation. That as the universe began to expand, it also began to cool. In the first trillionth of a second, temperatures soared above 1,000,000 billion degrees. These were conditions so extreme that ordinary matter could not exist. Instead, the universe was a soup of pure energy, a seething quantum foam. Particles and antiparticles flickered in and out of existence, colliding and annihilating each other in flashes of radiation. For reasons not yet fully understood, matter gained the tiniest edge over antimatter, a slight imbalance that would prove critical. The surplus matter would go on to form everything we see today. In those first moments, the rapid expansion of space smoothed out irregularities, spread energy evenly, and laid down the seeds for cosmic structures. Yet what is most striking about the Big Bang is how it transformed absolute simplicity into complexity. Out of near uniformity, patterns would emerge. Out of chaos, order. The universe's expansion has never stopped. In fact, every galaxy we observe today is moving away from every other galaxy, a discovery made by Edwin Hubble in the 1920s. Hubble's observations of redshifted light from distant galaxies confirmed the predictions of general relativity, Einstein's groundbreaking theory of gravity. The further away a galaxy is, the faster it recedes, a direct consequence of space itself stretching since the Big Bang. This became one of the strongest pieces of evidence for the Big Bang theory. Another line of evidence comes from the faint glow that still permeates the cosmos, the cosmic microwave background radiation. Discovered accidentally by Arno Penzias and Robert Wilson in 1965. This radiation is the afterglow of the Big Bang, a whisper from when the universe was only about 380,000 years old. It reveals a time when the cosmos cooled enough for atoms to form, allowing light to travel freely through space. Today, we can still detect this ancient light as a uniform, low-energy signal across the sky, a snapshot of the infant universe. Skeptics once proposed alternatives, such as the steady-state model, which suggested the universe had always existed in roughly its present form. But the mounting evidence for expansion and the cosmic microwave background dismantled such ideas. The Big Bang not only explained what we see, it predicted what we should see, and observations matched the predictions with uncanny precision. Yet, the term Big Bang itself can be misleading. It conjures images of a colossal detonation, but the reality is subtler and stranger. The event was not an explosion of matter in space. It was the rapid expansion of space itself. Galaxies are not flying through space as shrapnel. Rather, space itself is stretching, carrying galaxies along like raisins in rising dough. There is no center of the universe. no point from which everything expands. Every location is moving, away from every other, because the very fabric of space-time is growing. Cosmologists have tried to look back as close to the Big Bang as possible. With particle accelerators like the Large Hadron Collider, they recreate high-energy conditions similar to those of the early universe, seeking clues to how matter first took form. Observations of the cosmic microwave background allow us to map fluctuations that later grew into galaxies and clusters. Each discovery is like peeling back another layer of the universe's birth story. Still, mysteries abound. What set off the Big Bang in the first place? Did time itself have a beginning? Or was there something before? Some theories suggest that our universe may be just one in a multiverse of countless others, each with its own laws of physics. Others propose that the Big Bang might have been a bounce, following the collapse of a previous universe. These ideas are speculative, but they highlight the profound questions that remain. The Big Bang is not just a scientific theory, it is a narrative of origins. It tells us that everything, from the smallest atom in your body to the largest galaxy in the sky, shares a common ancestry. The iron in your blood, the oxygen you breathe, the carbon that forms life all trace their lineage back to that first moment of creation. To reflect on the Big Bang is to reflect on our own place. In the cosmos, we are, in a very literal sense, children of the universe's birth. Even though the concept can feel abstract, its reality is written across the sky. Every star, every planet, every photon of light tells the same story, that once, long ago, all was compressed into a singular beginning, and from that beginning came everything. The Big Bang is both humbling and empowering. Humbling, because it reminds us of how small and fleeting we are in the cosmic timescale. Empowering, because it shows us that we are part of something unimaginably vast, and yet understandable through the human pursuit of knowledge. As we look further into the depths of space, we are also looking further into the depths of time, back toward that singular moment when the universe was born. The light of distant galaxies takes billions of years to reach us. So in observing them, we witness the universe as it was long ago. In this way, every telescope is a time machine, carrying our minds closer to the beginning, closer to the first instant when the universe's story began. The Big Bang is not just the first chapter, it is the foundation of every chapter that follows. Without it, there would be no stars, no galaxies, no Earth, and no life to contemplate it all. It is the ultimate origin story, one that science continues to refine with every new discovery. After the initial burst of creation known as the Big Bang, the universe entered an extraordinary phase of transformation called cosmic inflation. If the Big Bang can be imagined as the birth itself, then cosmic inflation was the universe's rapid and explosive growth spurt, a brief but critical moment that defined much of what we see today in the cosmos. This expansion did not take place over eons, centuries, or even seconds in the sense we normally understand them. It occurred in a fraction of a second, so small that it defies ordinary comprehension. In that fleeting instant, the universe expanded, faster than the speed of light, stretching from subatomic size to something unimaginably larger. Cosmic inflation was first proposed in the early 1980s by physicist Alan Guth, who was trying to solve several nagging puzzles that the simple Big Bang model could not explain. For example, why does the universe look so uniform in all directions, even though light would not have had time to travel between distant regions? To even out their temperatures, this is called the horizon problem. Why is the geometry of the universe so close to perfectly flat, meaning that the total energy density is almost exactly balanced between expansion and collapse? That is the flatness problem. And finally, why don't we see magnetic monopoles? Hypothetical, heavy particles predicted by grand unified theories that should have been abundant. After the Big Bang, inflation offered elegant solutions to all these problems at once. According to the inflationary model, the early universe contained a peculiar form of energy stored in a quantum field, often called the inflaton. This field had the unusual property of creating a repulsive force, driving space to expand exponentially for a vanishingly small moment, roughly between K-36 and 10 to 32 seconds. After the Big Bang, the inflaton field dominated the universe. During this time, the size of the universe doubled over and over again in a runaway cascade. By the end of inflation, the universe may have expanded by a factor of 1026 or more. To put this into perspective, something smaller than a proton balloon to larger than a galaxy in less time than it takes light to cross the width of an atom. This sudden stretching had profound consequences. First, it smoothed out any irregularities. Imagine blowing up a balloon. As the surface expands, any bumps or wrinkles flatten out. In the same way, inflation ironed out the wrinkles of the early universe, leaving behind the striking uniformity we observe today in the cosmic microwave background. This explained why distant regions of space look nearly identical in temperature and structure, even though, without inflation, they would have been causally disconnected at the same time. Inflation magnified tiny quantum fluctuations, random jitters at the subatomic level into cosmic scale ripples. These microscopic irregularities became the seeds of all future structure in the universe. Where there was slightly more density, gravity eventually pulled in matter, leading to the formation of galaxies, stars, and planets. In this way, the universe's large-scale structure, its web of galaxies and clusters, is a direct imprint of the faint fluctuations generated during inflation. Incredibly, quantum physics and the vastness of the cosmos are linked through this process. Without quantum randomness, there would be no galaxies, no stars, and no life. When inflation ended, the inflaton field decayed, releasing its stored energy into ordinary particles and radiation in a process called reheating. The universe became a hot, dense plasma once again, filled with a roiling soup of quarks, electrons, photons, and other elementary particles. This set the stage for the next phases of cosmic evolution, including the formation of atomic nuclei and eventually atoms themselves. Evidence for inflation comes from observations of the cosmic microwave background radiation. In 2003, NASA's Wilkinson Microwave Anisotropy Probe WMAP mapped tiny variations in the CMB across the sky, later confirmed in exquisite detail by the European Space Agency's Planck satellite in 2013. These maps revealed a universe that was indeed remarkably smooth, but with just the right amount of irregularity, exactly what inflation predicts. The fluctuations in temperature, only about 1 part in 100,000, correspond to the tiny density differences inflated from quantum scales. Without them, the universe would remain a featureless fog. Still, inflation is not without mystery. The exact nature of the inflaton field remains unknown, as does the trigger that started and stopped inflation. Some versions of inflation suggest that it may not have been a one-time event. In eternal inflation models, inflation continues in some regions of space, creating a multiverse, a cosmic landscape of countless universes, each potentially with its own laws of physics. Our observable universe, in this scenario, is just one bubble among many, with new bubbles forming endlessly. While highly speculative, such ideas arise naturally from inflationary theory and continue to fuel debate among cosmologists. What makes cosmic inflation so striking is how it bridges the smallest and largest scales of reality. Quantum fluctuations, governed by uncertainty at the tiniest scales, became the blueprint for galaxies stretching millions of light years across. Inflation demonstrates the interconnectedness of physics, where the quantum realm and the cosmic expanse are part of the same story. If for a moment, try to imagine standing at the edge of time, watching the universe balloon outward faster than light itself. Galaxies that would one day sparkle with billions of stars were, in that instant, nothing but imperceptible ripples in an invisible field. Yet inflation took those ripples and stretched them across the sky, imprinting them onto the very fabric of spacetime. Without inflation, the universe as we know it might not exist. It solved critical puzzles, provided the seeds for cosmic structure, and offered a coherent link between the quantum and the cosmic. Though questions remain, the theory of inflation is one of the most remarkable achievements in human thought, a window into a time so close to the beginning that even light itself had scarcely had a chance to move. The universe, having undergone its growth spurt, was now vast, uniform, and filled with potential. From here, the story would continue with the emergence of fundamental particles, the building blocks from which atoms, stars, and galaxies would one day rise. Inflation ended, but the universe's expansion never ceased. It continues even now, billions of years later, carrying us further into the future, away from that first shimmering instant of creation. When the curtain of inflation drew to a close, the universe found itself in a radically new condition. Space had ballooned to an immense size, smooth and nearly uniform, but it was not empty. Instead, it was filled with a searing plasma, an ocean of energy, giving birth to the very first building blocks of matter. This era, which unfolded within the first few seconds after the Big Bang, was dominated by the formation of fundamental particles. Every atom, every star, every galaxy that would eventually appear was rooted in the physics of these moments. To understand how our universe took shape, one must follow the story of quarks, electrons, neutrinos, and photons as they emerged out of the furnace of creation. In the earliest instance, after inflation ended, the temperature of the universe was so staggeringly high, trillions of degrees, that matter could not exist in the forms we know today. Instead, energy constantly transformed into particles and antiparticles, and back again, in a ceaseless dance dictated by Einstein's equation, E equals mc. For every electron that flickered into existence, there was a positron, its antimatter counterpart. For every quark that appeared, an antiquark accompanied it. These pairs annihilated each other in flashes of radiation, only to be recreated by the energy saturating the cosmos. The universe was in balance, a fiery equilibrium where matter and antimatter seemed equally matched, yet something subtle tipped the scales. For reasons still not fully understood, there was a tiny asymmetry in nature that allowed slightly more matter to exist than antimatter. About one extra particle of matter for every billion matter. Antimatter pairs, as the universe cooled and annihilations played out, most matter and antimatter destroyed one another, releasing vast amounts of energy in the form of photons. But that tiny imbalance left behind a surplus of matter, the matter that would eventually form stars, galaxies, and life itself. Without this sliver of advantage, the universe would be filled with nothing but light, devoid of the substance necessary for complexity. Quarks were among the earliest fundamental particles to form. They are the constituents of protons and neutrons, the particles that make up atomic nuclei. At first, quarks roamed freely in the blistering quark-gluon plasma, a state of matter so exotic that it could only be recreated in high-energy particle accelerators billions of years later. But as the universe cooled to below 1 trillion degrees, quarks began binding together under the influence of the strong nuclear force. They combined in threes to form protons and neutrons, or in pairs to form mesons. This process marked a turning point. Matter was beginning to take on forms more familiar to us. Electrons, meanwhile, also appeared in abundance. These lightweight particles carried negative electric charge and were destined to orbit nuclei. Once atoms could eventually form, alongside them came neutrinos, elusive particles with no charge and tiny masses, which interact so weakly with other matter that they now stream through the cosmos almost unimpeded. In fact, trillions of neutrinos pass through your body every second, a silent echo of this formative era. As these particles emerged, they engaged in a frenetic struggle with photons, the particles of light. In the early universe, photons collided constantly with electrons and other charged particles. Scattering in all directions, the cosmos was opaque, a fog through which light could not travel freely. It would take hundreds of thousands of years before the universe cooled enough for atoms to form, finally releasing photons into open space. But even in this early epoch, light and matter were inextricably bound, shaping the conditions of the cosmos that followed. The interactions of these fundamental particles were governed by the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the earliest instance, some of these forces may have been unified, splitting into distinct interactions as the universe cooled. The weak nuclear force, for example, mediated the transformations between protons and neutrons, determining the ratio of these particles that would later influence how much hydrogen and helium would form. This period of fundamental particle formation was a cosmic balancing act. Too many neutrons compared to protons, and the chemistry of the universe would be very different. Too few and heavy elements might never form. The delicate ratios set during these first seconds became the foundation upon which all future cosmic chemistry was built. Our modern understanding of this era comes not only from theoretical physics, but also from experimental evidence. Particle accelerators like CERN's Large Hadron Collider recreate conditions similar to those of the early universe by smashing particles together at near light speeds. These experiments give us glimpses into how quarks behave in high energy plasmas, how particles acquire mass, and why matter may have triumphed over antimatter. Though we cannot travel back to the universe's first seconds, we can simulate its conditions in laboratories, peeling back the layers of cosmic history. It is staggering to think that the vast complexity of today's universe, spiral galaxies, planetary systems, and conscious beings originated in this stew of elementary particles. At the time, there was no structure, no order, only a furnace of creation where simplicity reigned. Yet within that simplicity lay the potential for everything. Each quark, each electron, each neutrino was a note in a cosmic symphony that would play out over billions of years. Consider for a moment the significance of these tiny building blocks. The protons and neutrons forged in the first seconds of the universe still exist today. They form the nuclei of the atoms in your body, the stars in the sky, and the dust that drifts between galaxies, the electrons that came into being in that. Early plasma still orbit the nuclei of every atom in existence. The particles are ancient, older than any star, older than any galaxy, carrying with them the memory of the universe's fiery youth. Thus, the birth of fundamental particles was not merely a phase of cosmic history. It was the foundation of all history. It established the ingredients from which all structure, chemistry, and eventually life would be built. The quark-gluon plasma cooled into protons and neutrons. Electrons awaited their chance to join them. Neutrinos slipped silently into the background. Photons blazed through the fog of plasma, awaiting the day when they could shine freely. The universe was only seconds old, but the groundwork had been laid. The next great chapter would come with the synthesis of simple elements, as protons and neutrons bound together into the first atomic nuclei. From there, the cosmos would march steadily toward complexity, building layer upon layer until stars, ignited and galaxies swirled. Yet none of it could have occurred without these first particles. The primordial alphabet of creation etched into existence in the earliest heartbeat of time. As the fiery seconds of the early universe stretched onward, the stage was set for one of the most pivotal transformations in cosmic history. The birth of the first simple elements. The fundamental particles, protons, neutrons, and electrons were already in existence, swirling within a dense plasma of photons and neutrinos. But matter as we know it, the stuff of stars, planets, and life, requires more than just these elementary pieces. It requires atoms, and atoms require nuclei. This is where the process of Big Bang nucleosynthesis comes into play. Roughly 1 second after the Big Bang, the universe was still unimaginably hot, around 10 billion degrees Kelvin. At these temperatures, protons and neutrons were colliding constantly, but most of their unions were ripped apart almost immediately by the violent energy around them. Yet as time passed, the expansion of the universe caused the temperature to fall, and by the time it reached about 1 billion degrees, only a few minutes after the Big Bang, protons and neutrons could finally cling to one another long enough to form stable nuclei. The first and most abundant element to form was hydrogen, the simplest of all. Consisting of just one proton, hydrogen became the primary building block of the cosmos, making up about 75% of all ordinary matter by mass. Without hydrogen, stars could never ignite, because hydrogen fusion is the fuel that powers them. Alongside hydrogen, helium was born specifically. Helium-4, composed of 2 protons and 2 neutrons. About 25% of the ordinary matter in the universe condensed into helium. Traces of other light nuclei, like deuterium, a heavy form of hydrogen with 1 proton and 1 neutron, helium-3, and lithium-7 also formed, though in far smaller quantities. The balance of elements created during this brief window was not random. It was determined by the ratio of protons to neutrons at the time. Early on, neutrons and protons could freely transform into one another via weak nuclear interactions. But as the universe cooled, these reactions froze out, leaving about 1 neutron for every 7 protons. This ratio dictated the eventual composition of elements. Too many neutrons, and the universe would have been saturated with helium. Too few, and hardly any helium would exist at all. The universe struck just the right balance, leaving behind the precise mix of hydrogen and helium that would allow stars to form and evolve. It is astonishing to realize how narrow the conditions for this synthesis were. The temperature had to drop at just the right pace, not so fast that neutrons decayed, before binding into helium, but not so slow that all neutrons were lost. The density of matter had to be finely tuned as well. A universe with slightly different starting conditions might have ended up devoid of stars or rich chemistry, an empty expanse of photons with little complexity. Yet our universe threaded that delicate path, and in the span of just a few minutes, it forged the elemental canvas upon which cosmic history would unfold. This brief period of nucleosynthesis lasted only about 20 minutes. After that, the universe cooled too much for nuclear fusion to continue, and the synthesis of elements effectively froze. Heavier elements like carbon, oxygen, and iron could not yet form because they required much higher densities and longer fusion cycles than the early universe could provide. Those would come much later, in the hearts of stars. For now, the cosmos was left with a simple palette: hydrogen, helium, and a faint trace of lithium. These were the raw ingredients of the first stars and galaxies, and eventually of life itself. Evidence for this process is written across the universe today. When astronomers measure the abundances of light elements in ancient gas clouds and distant galaxies, they find them to be remarkably consistent with the predictions of Big Bang nucleosynthesis. About 3/4 hydrogen, 1/4 helium, and mere slivers of deuterium and lithium, exactly as the theory foretells. These observations serve as one of the strongest confirmations of the Big Bang model. No other explanation accounts so elegantly for the primordial mix of elements that we still observe billions of years later. Consider the significance of this moment in the grand story. Every star that would later sparkle into existence relied on the abundance of hydrogen. Every planet with oxygen, carbon, and nitrogen in its atmosphere could only exist because the early universe created a foundation of lighter elements. Even the water you drink today owes its hydrogen atoms to those first moments after the Big Bang. Unchanged across 13.8 billion years, the helium-filling balloons at a child's birthday party is the same. Helium formed minutes after time itself began. From a narrative perspective, Big Bang nucleosynthesis was the universe's first act of alchemy. Out of the raw heat and density of creation, it produced something stable, something enduring. The transition from a sea of particles to actual atomic nuclei was like the first words written on a blank page, setting the tone for the story yet to come. It was the first step toward chemistry, the first step toward stars, and the first step toward the possibility of life. Yet it is also a reminder of how fleeting opportunities can be in the cosmos. The universe had only a narrow window, mere minutes, to forge these elements. Once the temperature fell below a critical threshold, nuclear reactions shut down, leaving the elemental ratios fixed for all time. What was made in those moments would remain unchanged until stars ignited billions of years later. To continue the work, scientists often describe this period as one of primordial cooking, though it was less a gentle simmer and more a furious fusion furnace. Still, the metaphor captures the essence. The universe gathered its ingredients early, like a chef laying out supplies before a great feast. Without that preparation, the later courses, the galaxies, the planets, the living beings who would one day ponder their origins, could never have been served. By the time the universe was just 20 minutes old, the age of element making was over. The cosmos was still hot, dense, and filled with radiation, but the chemistry of the future had already been written. Hydrogen and helium would dominate the story. Lithium would play its small part, and everything else would have to wait for stars to arrive and ignite, From here, the universe would enter a long period of cooling and expansion, setting the stage for atoms to assemble and light to finally break free. But it is in these first nuclei that we find the roots of everything: the silent, enduring testimony. That complexity begins with simplicity, and that from fire can come stability, balance, and beauty. The universe, now enriched with the first nuclei of hydrogen, helium, and traces of lithium, continued to expand and cool. The frantic fusion that had defined the first few minutes after the Big Bang subsided, and with it came a shift in the tempo of cosmic history. From this point onward, the story was no longer one of furious nuclear reactions, but of patience. The universe entered an age of cooling and waiting, a long interval before stars, galaxies, or any recognizable structures would appear. This was the cosmic interlude in which the conditions for the future were quietly laid down. At about 20 minutes old, the universe was still scorching hot, though far cooler than it had been moments earlier. Its temperature hovered in the range of hundreds of millions of degrees. A searing plasma of protons, electrons, helium nuclei, neutrinos, and an ocean of photons colliding endlessly. These photons scattered off free electrons, preventing light from traveling in straight paths. The cosmos was opaque, a fog through which no light could escape, unlike the transparent space we see today. This early universe was more like the glowing interior of a star, bright, hot, and blinding from within, but impenetrable from without. As expansion continued, the temperature steadily dropped. After 1 second, it was about 10 billion degrees. After a few minutes, it was down to 1 billion. By the time the universe was thousands of years old, it had cooled to just a few thousand degrees. Cooling changed everything, because temperature dictated what kinds of interactions could occur. At the highest energies, collisions between particles were so violent that nothing stable could form. But as the furnace dimmed, protons and neutrons held together as nuclei, electrons orbited them more loosely, and eventually, atoms themselves would become possible. But this would take time, hundreds of thousands of years. For now, the universe existed in what physicists call the photon epoch, dominated by radiation rather than matter. Photons vastly outnumbered the nuclei and electrons, and their interactions kept matter from clumping together. The energy of photons continually knocked electrons away from nuclei, preventing atoms from forming. This era was one of waiting. The matter was ready, but the conditions were not yet gentle enough for true structure to appear. During this vast stretch, something subtle and essential was happening. Tiny fluctuations in density, those quantum ripples inflated to cosmic scales, were beginning to grow under the pull of gravity. Regions that were ever so slightly denser than average attracted more matter, slowly becoming seeds for galaxies and clusters. The universe was remarkably uniform overall, but these minute differences set the stage for all future structure. Without them, everything would have remained evenly spread, a featureless fog. The cosmic web we see today, with galaxies strung along filaments like jewels, had its roots in these faint imbalances. Neutrinos, produced in enormous numbers during the first seconds, had by now decoupled from matter, streaming freely through space. They carried away energy, cooling the universe further, though their presence would become nearly invisible. Today, this cosmic neutrino background remains, a ghostly relic of the early cooling, though it is so difficult to detect that only indirect evidence confirms its existence. These neutrinos, along with the photons of the cosmic microwave background, form a silent chorus from the universe's infancy, forever traveling through space. The rate of cooling was not random. It depended on the balance of energy in the universe: matter, radiation, and possibly dark energy. Gravity worked against expansion, pulling matter inward. But the initial thrust of the Big Bang and the sheer abundance of radiation carried expansion forward. For hundreds of thousands of years, radiation remained the dominant force, keeping matter from clumping too tightly. It would take until about 380,000 years after the Big Bang for matter to finally gain the upper hand. When the universe cooled enough for electrons to bind with nuclei, forming the first neutral atoms, that event, called recombination, marked the release of light and the birth of the cosmic microwave background. But before that great unveiling, the universe was still in its shadowy, opaque youth. The cooling also allowed for stability. Neutrons, unstable when free, decay with a half-life of about 10 minutes. Yet those locked inside helium nuclei were preserved, ensuring that helium would remain abundant. Without the right rate of cooling, those neutrons might have been lost, leaving a universe of nearly pure hydrogen. Instead, the balance held, and helium endured as a cornerstone element, ready to fuel the first stars billions of years later. To imagine this era, one might picture an immense ocean of glowing plasma, stretching endlessly in all directions, neither light nor dark, neither transparent nor solid. The universe was filled with sound waves, oscillations of matter and radiation, bouncing off each other in rhythmic patterns. These acoustic waves left imprints we can still detect today in the cosmic microwave background, subtle variations in density that trace the vibrations of this youthful cosmos. The universe, in a sense, was humming to itself, its primordial music, carried forward in the patterns of galaxies and clusters we now observe. This cooling epoch may appear uneventful compared to the dramatic birth of particles and elements, but it was vital. It was a period of stabilization, where the chaos of the earliest seconds gave way to a calmer, more predictable environment. Without cooling, atoms could never have formed, photons would never have escaped, and the universe would remain a dense fog forever. Cooling turned energy into matter, matter into structure, and structure into the possibility of everything that followed. The beauty of this chapter lies in its patience. Cosmic time unfolded not in seconds or minutes, but in millennia. For hundreds of thousands of years, the universe was simply expanding and cooling, preparing itself for the great transitions yet to come. It is in this quiet interval that the story of galaxies, stars, and planets found its foundation. The cooling was the silent hand that guided the universe toward complexity, shaping the path from a hot plasma to a cosmos filled with light. By the end of this long cooling process, the universe was ready for its next milestone. Atoms would soon form, and light would finally break free, leaving behind the first visible imprint of creation. That light, stretched across billions of years, still reaches us today, carrying with it the memory of the universe's earliest breath of transparency. Roughly 380,000 years after the Big Bang, the universe reached a turning point that changed everything. Up until this moment, space had been filled with a dense, opaque plasma of protons, electrons, and photons colliding in a chaotic dance. Light could not travel freely because photons scattered off free electrons at every turn. The cosmos resembled a glowing fog, bright from within yet impenetrable, with no transparency and no possibility of stars or galaxies shining through. But as the relentless expansion cooled the universe to about 3,000 degrees Kelvin, similar to the surface of a red-hot star, something remarkable happened. Electrons finally settled into stable orbits around nuclei, forming the first neutral atoms. This process, known as recombination, was not a sudden flash but a gradual transition. As electrons bonded with hydrogen and helium nuclei, the density of free electrons plummeted. With fewer electrons to scatter off, photons began to stream freely through space for the first time. The fog lifted, and the universe became transparent. Those first photons, set loose on their eternal journey, are still traveling today. Over billions of years, the expansion of the universe has stretched their wavelengths into the microwave region of the spectrum. We now observe them as the cosmic microwave background (CMB), a faint afterglow from the moment the universe first revealed its face. The CMB is one of the most profound discoveries in cosmology. Detected in 1965 by Arno Penzias and Robert Wilson, who initially mistook it for interference caused by pigeon droppings in their antenna. It became undeniable proof of the Big Bang. This relic light permeates the cosmos uniformly, yet not perfectly. When viewed in exquisite detail by satellites like COBE, WMAP, and Planck, the CMB reveals tiny variations in temperature, differences of only a few millionths of a degree. These minute fluctuations correspond to the seeds of structure, the imprints of those primordial density ripples amplified during inflation. To understand their importance, imagine the early universe as a canvas. Without variation, no galaxies, stars, or planets would ever have formed. Everything would have remained smooth and featureless. But the tiny differences in density, slightly denser patches attracting matter more strongly, eventually grew into the grand architecture of the cosmos. Clusters of galaxies, vast cosmic filaments, and yawning voids are all echoes of those original fluctuations, fossilized in the microwave background. The release of the CMB also marked the beginning of a universe dominated by matter rather than radiation. Before recombination, photons carried the greatest influence, scattering particles apart and preventing them from clumping effectively. Once photons decoupled from matter, gravity was free to do its quiet work. Atoms of hydrogen and helium began to drift, gathering under the pull of denser regions. The framework for galaxies was laid down, though it would take millions of years before the first stars ignited. It is striking to consider that the universe we see through telescopes today still bears the faint light of this era. When we look at the CMB, we are not merely peering across space, we are looking back in time, to the very moment the universe first became transparent. This makes the CMB the ultimate photograph of creation, capturing the cosmos in its infancy. Unlike any other kind of astronomical observation, which reveals light from stars or galaxies formed later, the CMB shows us a universe without stars, without galaxies, just a fog of atoms settling into neutrality. The subtle patterns of the CMB also provide cosmologists with an extraordinary tool to measure the properties of the universe. By analyzing the distribution of temperature fluctuations, scientists can infer the density of matter, the proportion of dark matter and dark energy, the rate of expansion, and even the shape of the universe itself. In this way, the microwave background acts like a cosmic Rosetta Stone, encoding the physics of the early universe in its faint, ancient glow. One might imagine standing in that early epoch, as the last photons scattered and then suddenly broke free. The sky would have glowed a fiery orange-white, cooling toward red as expansion stretched the wavelengths. Slowly, over millions of years, that glow would have dimmed beyond visibility, fading into infrared and then microwave radiation. For any hypothetical observer, the cosmos would have seemed to pass from light to darkness. As no stars yet shone, it was a universe of silence and shadow. With the last great glow of the Big Bang fading into obscurity, this transition into transparency was not only visual but also structural. With electrons bound into atoms, the plasma soup ceased to dominate. The universe became more neutral, less chaotic, and more stable. Hydrogen, making up about 75% of the atoms, would serve as the fundamental fuel for the first stars. Helium, about 25%, also waited silently, ready to participate in stellar furnaces. The simplicity of these elements belies the richness they would eventually create. From these humble beginnings, all complexity, carbon, oxygen, iron, life itself would emerge through stellar alchemy billions of years later. The cosmic microwave background also carries within it the first hints of the mysterious forces shaping the universe. Its patterns suggest that most of the cosmos is not made of ordinary matter at all. Instead, invisible dark matter provided the gravitational scaffolding around which ordinary atoms could gather, while dark energy, still poorly understood, influenced expansion on grand scales. In this way, the faint glow of the CMB offers not only a picture of the past, but also clues to the universe's deepest mysteries. By the time recombination ended, the universe was on the verge of a long cosmic night. The glow of the microwave background faded beyond visible light, leaving behind a universe dark to the human eye. No stars had yet been born, no galaxies yet assembled. This coming era, often called the Cosmic Dark Ages, stretched on for millions of years, a silent interlude before the drama of starbirth. But though the sky was dark, the seeds of light had already been planted. Gravity was gathering matter, pulling gas into invisible wells of dark matter, preparing to ignite the first beacons in the cosmic night. And so, with the release of the cosmic microwave background, the universe left behind its foggy childhood. For the first time, light could travel unimpeded, carrying with it the memory of the early cosmos. Today, every time we tune a radio telescope to those faint microwaves, we are listening to the echoes of that ancient light, whispers from nearly 14 billion years ago, after the cosmic microwave background was released and the universe became transparent, a long silence settled across the cosmos. This period, stretching from about 380,000 years after the Big Bang to roughly 100 to 200 million years later, is known as the cosmic dark ages. The name is apt, with no stars, no galaxies, and no sources of light beyond the fading glow of the microwave background. The universe was shrouded in darkness. To an observer, the heavens would have appeared pitch black, though filled with a thin, invisible gas composed primarily of hydrogen and helium atoms. It was a cosmic waiting game, with gravity slowly working in the background, preparing to transform emptiness into brilliance. During the Dark Ages, the universe was not static. Expansion continued relentlessly, driving galaxies to be farther apart. The density of matter gradually thinned, but slight variations, those faint imprints recorded in the cosmic microwave background, remained crucial. In regions where matter was slightly denser, gravity exerted a stronger pull. Hydrogen and helium gas began to drift inward, collecting into immense clouds, though this process was agonizingly slow compared to human scales. Across tens of millions of years, it laid the foundation for the first great structures. One of the key players in this silent era was dark matter, the mysterious, invisible substance that outweighs ordinary matter by more than 5 to 1. Unlike normal atoms, which interact with light and radiation, dark matter interacts only through gravity. That meant it had already begun clumping together long before recombination. By the time atoms formed, dark matter had gathered into massive halos, invisible wells of gravity dotting the universe. These halos became the scaffolding around which ordinary matter collected. Without dark matter's silent architecture, the collapse of gas into stars and galaxies might never have happened, or would have been delayed far beyond what we observe. As hydrogen and helium accumulated in these dark matter halos, the clouds grew denser, but the universe still lacked the spark of light. For millions of years, it remained in a kind of twilight limbo. If one could somehow float through this epoch, space would feel eerily empty, cold, dark, and silent, yet filled with potential. The only sign of the universe's future brilliance lay in the slow gravitational dance of gas falling inward, compressing under its own weight. Within these deepening pockets of density, gravity reached a tipping point. As clouds of hydrogen collapsed, they heated from compression. Pressure and temperature rose steadily in their cores. Eventually, some clouds became hot enough to ignite nuclear fusion, the same process that powers modern stars. This moment marked the end of the cosmic dark ages and the dawn of starlight. The first stars, called population 3 stars, were unlike the stars we see today. Formed entirely from hydrogen and helium, they lacked heavier elements like carbon, oxygen, and iron, which only later generations of stars would produce. Deprived of these cooling agents, the gas in primordial clouds could only condense into very massive stars hundreds of times the mass of our sun, perhaps even more. These giants lived fast and died young, burning with extraordinary brightness for just a few million years before exploding as supernovae. When the first of these colossal stars lit up, they pierced the universal darkness like sparks in a vast night. Their ultraviolet radiation began stripping electrons from surrounding hydrogen atoms, ionizing the gas once more. This era, known as cosmic reionization, transformed the universe. Regions around stars became glowing bubbles of ionized gas, expanding outward until they overlapped with others. Over hundreds of millions of years, the universe transitioned from dark to light, filled with networks of shining stars and the first galaxies. The birth of these early stars had consequences far beyond illumination. Their cores fused hydrogen into helium, and in their brief, explosive deaths, they created heavier elements: carbon, oxygen, silicon, ion, casting them into space. These elements seeded the cosmos with the raw ingredients for planets, oceans, atmospheres, and eventually life. In a sense, the first stars were cosmic forges, transforming simplicity into complexity. Without them, the universe would remain a barren expanse of hydrogen and helium gas, forever devoid of structure or meaning. It is remarkable to consider that our existence today traces directly back to those early stars. Every atom of carbon in our cells, every oxygen molecule we breathe, every grain of silicon in the rocks beneath our feet, all were born in the fiery hearts of ancient stars that lived and died, billions of years before the sun ever formed. We are, in a very literal sense, the children of starlight. But the cosmic dark ages were not only about the birth of stars, they also set the stage for galaxies. As stars clustered together in gravitational wells, they formed the earliest galaxies, small, irregular collections of light compared to the sprawling spirals and ellipticals we see today. These galaxies merged over cosmic time, colliding and combining to build the larger systems that now populate the universe. The majestic Milky Way itself was born from countless such mergers, tracing its ancestry back to those faint, primeval clumps of light. From the perspective of modern astronomy, probing the dark ages is one of the great frontiers because no visible light existed. Observing this era directly is extraordinarily difficult. However, scientists seek its fingerprints in the faint 21-centimeter radio signal emitted by neutral hydrogen, hoping to map the slow collapse of gas during those silent centuries. Instruments like the Square Kilometre Array and experiments dedicated to the epoch of reionization are poised to uncover the universe's hidden youth. Each discovery promises to bring us closer to understanding how darkness gave way to brilliance. In contemplating the dark ages, one cannot help but marvel at the patience of the cosmos. For nearly 200 million years, the universe was a silent expanse without stars, without galaxies, and without observers. Yet within that stillness, gravity was sculpting the raw materials, shaping destiny itself. From quiet beginnings came a burst of light so profound that it defined everything to come. The Dark Ages were not an ending, but a preparation, the womb of the cosmos, holding within it the promise of everything we know today. The universe, once cloaked in the darkness of the cosmic Dark Ages, had finally found its voice. When the first stars ignited, their light began spreading across space, transforming a silent, opaque cosmos into one filled with radiance. But stars alone could not tell the full story. Their clustering, their interaction with gravity, and their eventual organization into immense structures would be what shaped the universe into its present form. This chapter in cosmic history is about the birth of galaxies, the grand assemblies of stars, gas, dust, and dark matter that dominate the universe today. In the beginning, galaxies were small. The earliest galaxies, often referred to as proto-galaxies, were faint, irregular clumps of stars gathered around dense pockets of dark matter. Unlike the well-formed spiral and elliptical galaxies we see in the modern sky, these first systems were chaotic, small, scattered, and frequently colliding. They were like cosmic seedlings, destined to merge, grow, and evolve into the immense star cities we observe through telescopes. Gravity, as always, was the architect. Dark matter halos, invisible yet massive, acted as gravitational anchors. Baryonic matter, ordinary atoms of hydrogen and helium, was drawn into these halos, cooling and condensing to form the stars that would populate the galaxies. Every galaxy, large or small, was structured around such a halo, and this invisible framework determined its growth. Without dark matter, galaxies might never have coalesced at all, or would have been too fragile to survive the early violence of the universe. The first galaxies were tiny by modern standards, containing only a few million to a few hundred million stars. For comparison, our Milky Way house is about 200 to 400 billion stars. These primitive galaxies blazed with the light of massive, short-lived stars that had formed from pristine hydrogen and helium. Their radiation and supernova explosions played a crucial role in ionizing the intergalactic medium, slowly turning neutral hydrogen back into ionized gas. This process allowed light to travel freely through space, gradually clearing the cosmic fog. Over time, galaxies grew larger not only by forming new stars, but also through a process called hierarchical merging. Smaller galaxies collided and merged, their stars and gas combining to form progressively larger structures. These collisions were not gentle. They were violent interactions that could trigger massive bursts of star formation as gas clouds were compressed and ignited. Yet they were also essential to building the vast galactic systems we see today. Through billions of years of this process, the universe developed a grand cosmic web. Galaxies arranged themselves along immense filaments of dark matter, forming clusters and superclusters separated by vast cosmic voids. When astronomers map this structure today, it looks like a colossal three-dimensional spiderweb with galaxies glowing at the intersections. This web-like pattern reveals the deep influence of dark matter, which pulled galaxies into its invisible scaffolding and continues to shape their distribution. The diversity of galaxies also began to emerge during this period. Some evolved into spiral galaxies, with graceful arms curving outward from a central bulge. Like our Milky Way, spirals formed where there was enough angular momentum for gas and stars to settle into rotating disks. Others became elliptical galaxies. Massive, rounded systems formed through mergers that scrambled stars into random orbits. Still others remained irregular, small, and chaotic, lacking a clear shape. This diversity rose not from chance alone, but from the histories of collisions, environments, and interactions each galaxy experienced. As galaxies matured, they became engines of creation. Within them, stars continued to form, live, and die, enriching the surrounding gas with heavy elements forged in stellar cores. Each cycle of birth and death increased the abundance of elements like carbon, oxygen, silicon, and iron. With each new generation, stars and planets became more chemically complex, paving the way for environments where life could eventually emerge. The Milky Way itself underwent such enrichment for billions of years before the Sun and Earth were born. Central to many galaxies was another profound phenomenon: the emergence of supermassive black holes. Even in the early universe, massive black holes millions or billions of times the Sun's mass appeared in galactic centers. These behemoths influenced their host galaxies in profound ways, releasing jets and radiation as they fed on surrounding matter. They helped regulate star formation, shaping the destiny of their galaxies. Today, we find that nearly every large galaxy harbors a supermassive black hole at its core, a testament to their fundamental role in cosmic evolution. Modern astronomy allows us to glimpse these early galaxies with powerful instruments, like the James Webb Space Telescope JWST. For the first time, we can see galaxies as they appeared just a few 100 million years after the Big Bang, faint and redshifted by cosmic expansion. These observations confirm much of what theory predicted, that galaxies began small, merged over time, and gradually built the complex structures of today's universe. Each image we capture is a look back in time, showing us how galaxies assembled their light step by step. The birth of galaxies was more than a structural transformation of the universe. It was the beginning of cosmic order. Where once there had been diffuse gas, now there were luminous systems bound by gravity, shining across billions of light years. These galaxies became the homes for stars, planets, and eventually observers like us. Without galaxies, the universe would be a cold, dark sea of scattered atoms. With them, it became a vibrant, structured cosmos filled with the promise of complexity. As we reflect on this era, it is humbling to recognize that we live inside one of these magnificent structures. Our Milky Way is not just a backdrop, but a direct heir to those first proto-galaxies that assembled in the young universe. Its spiral arms, its billions of stars, and its quiet rhythm of star birth all trace back to the collisions, mergers, and gravitational sculpting that began more than 13 billion years ago. To study the birth of galaxies, then, is not merely to understand distant history, it is to glimpse the foundations of our own cosmic home. As the galaxies continued to take shape and the universe settled into its great cosmic web, a new and profound transformation began. The birth of stars and planets in the dense nurseries, scattered throughout galactic arms. If galaxies were the grand theaters of the universe, stars and planets were the actors that would fill the stage with stories of energy, matter, and, eventually, life. This stage of cosmic history marked the transition from a universe dominated by light and structure to one that began producing the building blocks of complexity. The earliest stars, the so-called population 3 stars, were unlike anything we see today, formed entirely from the pristine hydrogen and helium left over from the Big Bang. They contained no heavy elements, without carbon, oxygen, or metals to aid in cooling. The gas clouds from which they formed collapsed into much larger stars than we typically observe in the modern universe. Many of them may have been hundreds of times more massive than the Sun, burning at furious temperatures and living only a few million years before ending their lives in cataclysmic supernovae. These explosions were not just dramatic endings, but essential beginnings. In their fiery deaths, the first stars forged the universe's first heavy elements: carbon, oxygen, nitrogen, iron, and many more. These elements were scattered into interstellar space, mixing with the gas clouds that would later collapse into new stars. Each subsequent generation of stars thus became progressively richer in elements beyond hydrogen and helium, allowing the formation of planets, moons, and eventually the chemistry necessary for life. Star formation itself was, and remains, a remarkable process. Within galaxies, especially along their spiral arms, cold clouds of hydrogen known as molecular clouds served as stellar nurseries. Under the pull of gravity, clumps within these clouds collapsed, their cores heating up as pressure increased. Once nuclear fusion ignited in the core, a star was born. Depending on its mass, a star could shine for a few million years or several tens of billions. Small, cool red dwarfs burn their fuel slowly, while massive blue giants consume theirs in a cosmic blink. Around many of these young stars, something extraordinary occurred. Disks of gas and dust formed, swirling remnants of the material that did not fall into the star itself. Within these protoplanetary disks, tiny grains of dust collided, stuck together, and gradually built up into planetesimals. Over millions of years, these planetesimals merged into full-fledged planets. The process was chaotic, with frequent collisions, migrations, and rearrangements. But out of that chaos emerged the diverse planetary systems we now see across the galaxy. Our own solar system is just one example of this process at work. About 4.6 billion years ago, a molecular cloud in the Milky Way collapsed to form the Sun. Around it, a disk of dust and gas gave rise to 8 planets, dozens of moons, countless asteroids, and comets. The Earth, in particular, formed from the accumulation of rocky material, its crust seeded with elements that had been forged in countless supernovae over billions of years. Every atom of calcium in our bones, every molecule of oxygen we breathe, every grain of iron in the ground, all were created in stars that lived and died long before our Sun. As telescopes have improved, astronomers have discovered that planets are not rare but common. Thousands of exoplanets have been identified orbiting other stars with an astonishing diversity. Hot Jupiters orbiting perilously close to their suns, super-Earths larger and more massive than our planet, water worlds covered entirely in oceans, and strange icy giants with exotic atmospheres. These discoveries confirm that planet formation is a natural byproduct of star formation and suggest that the universe may be filled with billions of habitable worlds. The birth of stars and planets also marked a new chapter in cosmic enrichment. Stars continue to forge heavier elements throughout their lifetimes. When low to medium mass stars like the Sun die, they shed their outer layers into space, creating planetary nebulae that enrich the interstellar medium with carbon and nitrogen. When massive stars explode as supernovae, they hurl vast amounts of iron, silicon, and even rarer elements into space. Each new generation of stars and planets, therefore, forms from material more chemically diverse than the last. In this way, the universe became a chemical tapestry. From hydrogen and helium, it wove oxygen for breathing, carbon for life, silicon for rocks, and iron for blood. Without this cycle of star birth and death, the universe would be sterile. Instead, it grew richer with every passing eon, until the conditions for life as we know it became possible. The process of planetary system formation also introduced a kind of cosmic filtering. Not every star would host planets, and not every planet would be habitable. Some orbits would be unstable, others too close or too far from their star. Some systems would experience catastrophic collisions that destroyed planets or ejected them into interstellar space. Yet, among the countless failures, there were successes: stable, rocky worlds orbiting within the temperate habitable zone where liquid water could exist. Earth was one such world, but it was by no means unique. The birth of stars and planets thus represents both continuity and transformation. Continuity, because it is a process still unfolding today in the spiral arms of galaxies. Transformation, because it changed the universe from a place of gas and stars alone into a place with solid surfaces, oceans, atmospheres, and the raw ingredients of biology. The seeds of life itself were sown in these processes, though it would take billions of years before they blossomed into conscious beings, capable of pondering their origins. Looking out at the night sky, one sees not just points of light, but echoes of this long history. Every star we observe is both an ancient furnace and a potential cradle for worlds. Every planet discovered reminds us that the story of Earth is part of a much larger narrative, written across the cosmos. The birth of stars and planets was not the final act of cosmic creation, but rather the opening of a new chapter, one that would eventually give rise to oceans, forests, civilizations, and the very eyes reading these words. Word count 1106, waiting for continue. The birth of stars and planets had set the stage, but the story of the universe was far from complete. Over billions of years, the cosmos evolved into the vast, intricate structure we see today, a tapestry of galaxies stretching across unimaginable distances, bound together in a cosmic web of filaments and voids. This ongoing evolution was not a simple matter of stars shining and planets orbiting. It was a dynamic, ever-changing process of growth, collapse, and interaction. The universe was, and still is, alive with motion. At the grandest scale, the universe continued to expand as it has since the Big Bang. Galaxies drifted farther apart, carried by the stretching of spacetime itself. Yet within this expansion, gravity played its counterbalancing role, pulling matter together into clusters and superclusters of galaxies. The Milky Way, our home, is not isolated, but a member of the local group, a small cluster that includes the Andromeda Galaxy and dozens of smaller companions. Together, this group belongs to the Virgo supercluster, itself a tiny filament in the vast structure known as Laniakea, a web-like formation stretching over hundreds of millions of light years. The cosmic web, revealed by observations and simulations, is perhaps one of the most awe-inspiring discoveries of modern cosmology. Galaxies are not scattered randomly, but arranged along vast filaments of dark matter and gas, forming interconnected threads that span the universe. Between these threads lie immense voids, regions nearly empty of galaxies, giving the cosmos a sponge-like structure on unimaginable scales. It is in these filaments, where matter is most concentrated, that galaxies collide and merge, shaping the evolution of the universe. Over billions of years, galactic collisions, far from being rare, catastrophes are common events in cosmic history. Unlike car crashes, these encounters rarely involve direct collisions between stars, since the spaces between them are vast. Instead, the gravitational tides of colliding galaxies pull at each other, distorting their shapes, igniting bursts of star formation, and sometimes merging into entirely new galaxies. Our own Milky Way is on a collision course with the Andromeda Galaxy, and in about 4 billion years, the two will merge into a massive elliptical galaxy. For any life that survives to witness it, the night sky will blaze with spectacular patterns of stars, nebulae, and tidal streams. Meanwhile, within galaxies, the cycle of birth and death continued. Massive stars lived brief but intense lives before exploding in supernovae, enriching the interstellar medium with heavier elements. Smaller stars, like our Sun, burned more slowly, eventually shedding their outer layers and leaving behind white dwarfs. Neutron stars and black holes were left as remnants of the most massive stellar explosions, each becoming strange laboratories of extreme physics. Black holes, in particular, emerged as not just endpoints of stellar death but as engines of galactic evolution, regulating star formation through powerful jets and winds. Planets, too, evolved. Some cooled into barren rocks, others retained thick atmospheres, and some developed conditions suitable for liquid water. A fraction of these, like Earth, nurtured chemistry complex enough to spark life. The appearance of life added an entirely new dimension to cosmic evolution. matter that could replicate, adapt, and evolve. While Earth remains the only known planet with life, the vast number of exoplanets discovered suggests that life may be widespread, even if it takes different forms from what we know. As the universe aged, its energy budget also shifted. In the early universe, radiation dominated, followed by matter. Today, observations reveal that a mysterious force known as dark energy drives the accelerated expansion of the universe. This discovery, made in the late 20th century, changed our understanding of cosmic destiny. If dark energy continues to dominate, galaxies beyond our local group will eventually slip beyond our cosmic horizon, their light forever unreachable. Billions of years from now, distant observers may see only the faint glow of their local galaxies, unaware of the grand universe that once lay beyond. Yet even as expansion continues, the smaller scales remain rich with drama. Stars are still forming in dense clouds, planets are still emerging around young suns, and supernovae still light up galaxies like cosmic fireworks. Every second, somewhere in the universe, a star is born, another dies, and new elements are forged. The cycle continues, endlessly renewing the cosmos. On the horizon of time, the ultimate fate of the universe remains uncertain. If dark energy persists unchanged, expansion will continue indefinitely, leading to a heat death, where stars burn out, galaxies fade, and only cold remnants remain in an ever-stretching void. Alternatively, if dark energy evolves or changes, other fates are possible. A big rip tearing galaxies and atoms apart, or a big crunch reversing expansion and collapsing everything back into a singularity. These scenarios are still debated, but they remind us that the universe's story is not yet finished. For humanity, the cosmic evolution provides both perspective and purpose. We are latecomers in a universe 13.8 billion years old, yet we are also participants in its ongoing unfolding. The atoms in our bodies were forged in ancient stars. The Earth we stand upon is a product of billions of years of planetary evolution. Looking to the future, we may one day carry life beyond Earth, seeding new worlds with the legacy of our planet. In doing so, we would continue the universe's tendency toward complexity and creativity. In the end, the evolution of the universe is not a simple tale of expansion and cooling, but a story of emergence. From a hot, dense beginning came galaxies, stars, planets, and life. From simplicity came complexity. From chaos came structure. And from silence came consciousness capable of reflecting on it all. The cosmos, vast and indifferent though it may seem, has given rise to beings who can ask where it came from and where it is going. That is perhaps its most remarkable achievement.